You are watching one of a series of videos giving an introduction to OrcaFlex. The first 4 of these videos, which we've called the fundamentals, are those that we would regard as prerequisites for looking at any of the other subsequent topics. If you are already familiar with these fundamentals, you may want to pick and choose the subsequent videos you watch based on your area of interest. If you're a complete beginner with OrcaFlex, I would strongly encourage you to watch the full series in order, as this will give you a good basic overview of the program, how to navigate it, and where to access and input data. It goes without saying that the quality of any OrcaFlex analysis is only as good as the quality of the input data, and that, of course, relies on the skill and experience of you, the user. These videos will help you to learn how to use OrcaFlex as one of your analysis tools, and I do hope that you find them educational and maybe even a little bit enjoyable too. We are going to discuss in this video the buoy objects in OrcaFlex. As we can see from the toolbar, we have 2 types of buoys available in OrcaFlex, 3D and 6D buoys. They are rigid bodies and their hydrodynamics are given through Morrison's equation. Because of this, their size should be much smaller than the wavelength they experience. If this is not the case, then it is likely that diffraction effects will dominate, in which case a vessel object would be more suitable. As their names suggest, the fundamental difference between 3D and 6D buoys are their degrees of freedom. Note that, although called buoys, they do not need to be buoyant, so they can be used to model any rigid body whose motion you want to calculate. The 3D buoy is a simple point body that has 3 translational degrees of freedom. It cannot rotate and therefore can't transmit moments, and should be used for modelling objects that are small enough for rotations to be unimportant, such as a small body forming a pin connection between 2 lines. Its net buoyancy is determined by the mass and the volume. As with other OrcaFlex objects, we can see the submerged mass of a 3D buoy by looking at its properties report using the context menu or the shortcut Alt and Enter. The 3D buoy is represented in the 3D view by a vertical stick, the length of which is determined by the height on the dataform. Half of the height extends above and half below the buoy origin. If the buoy is surface piercing, the height will determine when the buoy starts to experience buoyancy forces. As the vertical stick starts to enter the water, buoyancy forces will start to take effect. We can see when a buoy is wet by looking at a result for dry length. Let's fix this 3D buoy at a Z value of 0, so directly on the sea surface. If we run dynamics and then look at a result for dry length, the y-axis shows the dry length ranging from 0 to 5 meters. Moving through the replay to a point when the buoy is fully submerged, we see the dry length is at the minimum of 0 meters. Conversely, at a point when it is fully above the water surface, the dry length is at the maximum of 5 meters, because this buoy has a height of 5 meters. You can see that the number of results available for a 3D buoy are quite limited, with most notably no rotational results. We can confirm the lack of rotation for this buoy by allowing it to be free in dynamics and then observing the behaviour. Note that we will have to turn off buoy degrees of freedom in statics to ensure statics solves with this indeterminate system. The response of this buoy is, as expected, only in translation. Moving now to 6D buoys, these are much more sophisticated than 3D buoys. They are rigid bodies with all 6 degrees of freedom, and OrcaFlex calculates their translational and rotational motion. Several different types of 6D buoy are available for modelling different sorts of marine object. The first type of 6D buoy is a lumped buoy. This is the default type used when you first insert a 6D buoy into a model, and it is represented by a cube with a series of edges and vertices. This is an arbitrary default shape which can be modified on the drawing page and optionally imported from a mesh file. The vertices are used to calculate the interaction of the buoy with shapes and the seabed, but do not affect the properties in any other way. As already specified, 6D buoys can rotate and transmit moments. If we run this dynamic analysis again, we can see the rotations now included in the 6D buoy as waves pass, compared with the translational motion of the 3D buoy. Although more sophisticated, the lumped buoy still handles surface piercing in a very simplistic way, with a single calculation point for hydrodynamics. On the 6D buoy data form, we have significantly more data than the 3D buoy, but its net buoyancy is still determined by the mass and the volume, with the height half above and half below the centre of volume determining the proportion wet. We can apply damping, drag and fluid inertia properties, as well as slam data to allow us to model the slam force as the buoy enters or exits the water. We can include supports on a 6D buoy, and these are discussed more in the video on shapes and contact. We can also include forces and moments from other effects, including Morrison elements, applied loads, and loads including friction from contact with the seabed or elastic solid shapes. If you want to remove contact between a 6D buoy and the seabed or elastic solid shapes, you need to set the contact area here to 0. Wings can be added to a 6D buoy to allow the inclusion of lift and drag forces to represent things like diverters. A wing with a certain span, chord, etc. is added on the wings page, and a table of coefficients versus incidence angle are added on the wing type data form. Moving to the drawing page, we've already discussed the shape of a lumped buoy being from a series of edges and vertices. This is a cube by default, but can be modified by the user on this page, including the option previously mentioned of importing a wireframe from a mesh file. The shaded drawing is, by default, a solid object. If an edge has a diameter value that is not the default tilde symbol, this will be drawn as a cylinder with the given diameter. This allows the visualization of parts of a structure that are not solid, such as a crane boom or manifold. We can see this by setting all the diameters in the default cube to 0.5 meters. Note that it is still a rigid structure. If you wanted to model a structure that could bend and flex, the individual edges would need to be modeled as lines connected together. Finally, one useful shaded drawing option is the ability to import an image file to more accurately depict a structure. There are some default image files provided with OrcaFlex, or you can import your own, which can be one of a number of file types shown here. I'll navigate to the OrcaFlex sample files and select a subsea template as an example. This can also be scaled to suit the application. There are two other types of 6D buoy: spar buoys and towed fish. These are essentially the same thing, with a towed fish being a spar buoy that has its principal axis horizontal instead of vertical. This allows easier modelling of towed bodies. So our subsequent discussion about spar buoys can also be applied to towed fish as well. As with lumped buoys, spar buoys can rotate and transmit moments, but they handle surface piercing in a more sophisticated way. Their geometry is defined as a series of stacked cylinders, and the buoyancy and hydrodynamic loads are calculated individually for each of these cylinders. The cylinders can be the same size or they can vary in length and diameter. Remember that for a lumped buoy, its hydrodynamics are calculated at a single point. These images show a surface-piercing spar buoy model as a single cylinder. OrcaFlex will look for the wave slope above or below the centroid of the cylinder and fit a tangent to the wave at that point to determine how much of the buoy will be treated as wet. If the buoy is inclined, this can result in an unrealistic proportion of the buoy being treated as wet, as indicated by the green portion of the buoy in this image. This can then result in inaccurate buoyancy calculations for shorter wavelengths. Contrast this with the same spar buoy modelled as a series of stacked cylinders. Now, with tangents calculated above or below the centroids of each cylinder, the proportion wet will be more realistic, leading to more accurate buoyancy calculations. We will now go through the process of building a model which compares the behaviour of the different types of buoy in a payload lowering scenario. The arrangement comprises a payload slung from a crane wire using two bridles. These bridles have differing lengths in order to demonstrate the differences in a model with and without rotations allowed, and we will build the arrangement with three different buoy types, allowing us to directly compare their responses as the payload passes through the water. Firstly, in a new OrcaFlex model, we'll make a global change to the environment data, setting the wave height to 0 so that we can focus only on how the payload buoyancy influences its response. We will also introduce the first line representing the crane wire. This will include line feeding data to lower the payload. It will be identical for all three instances, so, once created, it can be duplicated using the usual copy-paste methods. The data for the environment and the line are in the table on the screen. We'll insert a new line into the model and open its data form. This can be called 3D wire, and A is fixed at 0, 0, 19, and B is free at 0, 0, 8. The line length is 30 meters and segment length is 5 meters. On the feeding page, we'll set an initial arc length of 20 meters, which essentially puts 20 meters of the 30 meter length of line into an imaginary drum, meaning the initial active length of line in the model is 10 meters. We'll set a payout rate of 0.5 meters per second. All other properties can remain at their default values. Next, we will introduce the first payload, represented by a 3D buoy. For the 3D buoy, we will set the data shown in the table. It will be called 3D buoy and will be free at 0, 0, 2 with a mass of 30 tons and a volume of 7.854 cubic meters. This is the volume equal to the volume of the cylindrical spar buoy we'll be introducing shortly. It should have a height of 1 meter, with all other properties left at their default values. In reality, of course, we should also be setting suitable hydrodynamic properties, but in this case we are neglecting these for simplicity. Then we will introduce the first bridle line using a link object. This will be called 3D bridle 1 with end A connected to the end of 3D wire with an arc length of 0 relative to end B, and end B connected to the 3D buoy at a position of -5, 0, 0.5. Its unstretched length will be 6 meters with a stiffness of 100 E3 kilonewtons. The second bridle will be very similar to the first, so we can copy-paste it. On the 3D Bridle 2 data form, the end-B connection should be changed to 5 meters in X, and the unstretched length should be changed to 8 meters. At this point, we can run dynamics and view the payload passing into the water. The first obvious issue is that, despite the unequal length bridles, the payload hasn't rotated to compensate, because 3D buoys cannot rotate. This immediately rules out the 3D buoy for this specific application. We also see no resultant buoyancy effects as the payload passes into the water, again because it cannot rotate. OK, that's the first system. Let's go ahead and set that up as a group in the model browser. If you haven't already done so, View by Groups needs to be enabled in the Model Browser context menu. Next, we will add a group called 3D Buoy Group. And move all the objects into that group. Having done this, we can start the next group by copying and pasting the first group. Before we paste, select the top level of the folder structure to ensure the new group doesn't get pasted within the first group. We will rename this as the lumped group, and also rename the bridles and line. The 3D buoy obviously needs to be deleted, and we will insert a 6D lumped buoy in its place. The data for the lumped buoy is as per the table. Firstly, note that the new object is at the top level of the model browser, so we can drag and drop it into the lumped group. Note also that it is easy to reorder objects in a group if, say, we want to have a consistent object order like buoy, wire, bridles. I'll do this for the 3D buoy group as well by dragging the buoy above the line. This 6D buoy is to be called lumped buoy, and its initial position is 0, 0, 2. The default mass is 30 tons, which is what we require in this case, and the only mass moment of inertia to change is in the x direction, setting this to 10. On the properties page, the volume should again be 7.854 cubic meters, with a height of 1 meter. The only other change to the buoy is that of the drawing data. This doesn't influence its hydrodynamics. Remember, a lumped buoy has a single calculation point for buoyancy at the centre of volume. But it would have an effect if there was contact with the seabed. We will change the drawing data for visualization purposes using the vertex information in this table. I have this information in an Excel table, so it's very easy for me to copy and paste it. The final change to make with this arrangement is to connect the bridles to the new lumped buoy. On each link data form, select the lumped buoy as the new connection for end B. Because we have positioned the buoy first, the positional data will already be correct. We now have two complete arrangements and can run dynamics to look at the responses side by side. The arrangement with the 6D lumped buoy has rotated such that the centroid of the buoy is below the winch wire. However, there is still no apparent buoyancy response as the buoy enters the water. This is because of the simple buoyancy calculation performed at the centre of wetted volume of the lumped buoy. We can confirm this issue by reviewing a time history result for the dry length of the buoy. At a dry length of 1 metre for this buoy, because the height has been specified as 1 metre, the assumption is it is completely above the water. However, if we move through the replay until the point where the lower part of the buoy should be getting wet, and therefore experiencing buoyancy effects, the dry length result shows that it isn't. It is only when the portion of the buoy below its centre of volume moves into the water that the program sees it is getting wet. So, let's look at this arrangement built with a spar buoy, which allows us to discretize the buoyancy calculation to capture surface piercing effects in a more detailed way. Once again, we will copy the previous arrangement and paste it into the top-level model folder. And we'll rename the new folder and objects to relate to the spar buoy. The spar buoy should now be modified with the new data in this table. First, we'll change the type to spar buoy and change the initial position to -5, 0, 2 and rotation 2 to 90. Next, we will adjust the mass moments of inertia in X to 100 and in Z to 10 and position the centre of mass at 5 meters in Z. This is because the principal axis of the spar buoy is horizontal. Finally, on the geometry page, this buoy will be created with a stack of 10 cylinders, each with 1 metre diameter and 1 metre length. If I set the length to 1 metre, then increase the cylinder count to 10, this will give us the desired geometry. The final change in this arrangement is to reposition the bridles as detailed in the table, with bridle 1 being at -0.500 and bridle 2 being at -0.5010. We should now be able to run dynamics and view the response of all three arrangements side by side. It is only the spar buoy which responds as expected as it enters the water, since the wetted volume of a spar buoy is automatically calculated based on its cylindrical geometry. Let's look at a time history result for dry length again, for the spar buoy this time. We can see if we zoom in on the result that it starts to change as soon as the first cylinder enters the water, providing a much more accurate buoyancy calculation for this surface piercing scenario. Whilst we cannot automatically discretize the lumped buoy, as can be done with the spar buoy, it would also be possible to create this arrangement with 10 separate 1 metre lumped buoys connected together, thereby providing 10 separate sets of buoyancy calculations. This would, however, be extra work, and results reporting would not be so easy, since you would be dealing with 10 separate buoy objects, rather than one buoy object for the spar arrangement. I would encourage you now to save this model as a useful future reference. We're now going to build a simple single-point moored buoy model using the properties in this table. I would encourage you to pause the video at this stage and have a go at building the model yourself, and then I will run through it step by step on screen. Once again, whilst you should, for real cases, set appropriate hydrodynamic data, we will be ignoring it here for the sake of simplicity. So, starting with the environment data, the default water depth is 100 meters, so that doesn't need to change. Next, we need to set a 1 meter, 5-second wave and a 0.5 meter per second current, which needs to be constant for all depths, the default setting, and in the same direction as the waves, also the default setting. The next step is to build a chain mooring. To access the line type data, we need to introduce a line into the model. And because we are modelling a chain, we can use the line type wizard. Selecting the chain type and entering the bar diameter as 0.04 meters. All other line type properties are calculated by the wizard, including the setting to limit compression. Important because a chain cannot support compression. The line itself should be 110 meters long and called mooring. The default segment length is 10 meters, so we know already that this will probably be too long for this system if a significant amount of motion is expected. We'll set this to 1 meter. The line will be connected at end A to the buoy, yet to be created, but we can anchor end B for now. Its XY position isn't important, but I will position it at 0, 0, and with a height above seabed of 0. We'll come back to the line once we have the buoy, which we will create now. The default buoy type is the lumped buoy, but we have properties for a cylindrical body, which lends itself to the spar type. It is also surface piercing, and we now know that discretized spar buoys are much more suitable for accurately modelling surface piercing effects. On the geometry page, it needs to be 5 meters long and 2 meter diameter, but as we discussed, we should discretize the geometry. Let's use 5 1 meter long cylinders of 2 meter diameter. We also have some inertia properties, including a mass of 5 tons and mass moments of inertia of 12, 12, and 2.5. The centre of mass is given as 1 meter above the base on the centre line. So, the centre of mass should be 001, since the local origin of a spar buoy is at its base. The mass has been set, and the volume of a spar buoy is automatically calculated from the geometry. We can look at the properties report from the context menu to confirm that the buoy as a whole is net buoyant, with a negative submerged mass. The position of the buoy in the reset state isn't necessarily critical, but to start with, we will position it at 0, 0, 0. Finally, we can go back into the line data form and connect end A to the base of the buoy with coordinates of 0, 0, 0. If we run statics now, it is quite likely that we will see a singular Jacobian error. This means that the position or rotation of something in the model is indeterminate. There are 2 potential causes here, the first being that everything is perfectly aligned along the global z-axis, with the line being slack. When statics is run, it is not clear in which direction to apply restoring forces to the line because it is slack and lying in a mathematically but not realistically perfectly aligned position with the global z-axis. This is an example of a model where the positions of objects in the reset state can help provide some determinacy when the static calculation starts. Let's reposition the buoy to an x value of -30 meters. This puts the line into some tension at the start of statics. However, we still see the same error. A further example of object positioning leading to some indeterminacy is the fact that the buoy is sitting on the surface of the water. If something is going to be surface piercing, position it in the reset state accordingly. Let's move the buoy down by setting Z to 2.5 meters in the negative direction, thus ensuring buoyancy forces will be present at the start of statics. We still see this error, and there is one more common cause, and it is particularly common with rotational determinacy of 6D buoys. Again, we have perfect alignment of the buoy geometry, its centre of mass, and the connection of the mooring line. Because of this perfect alignment, there are an infinite number of valid rotational positions, and no indication which is the right one. One way we can guide the solver to a unique rotational position is to slightly offset the connection. For example, if we offset the connection of end A of the line by 0.001 meters, this should be enough to provide rotational determinacy for the solver without adversely affecting the global performance. We can now run dynamics, but a glance at the status bar suggests some spikes in iteration count as it runs, which we can confirm by looking at a time history. Viewing a properties report for the general object shows a runtime of around 3.6 seconds. Note that it may be a little different for you depending on the performance of your computer. This would be a good opportunity to consider whether this runtime can be improved by reducing the iteration count, something that a shorter dynamic time step can often help with. If I drop the time step down to 0.01 seconds on the dynamics page of the general data form, this will mean a greater number of calculations, but if this also drops the iteration count down, the number of calculations per time step, we may see an overall improvement. Sure enough, the runtime has fallen to around 2.3 seconds in my case. Just before we finish this video, I want to highlight a further option available in recent versions of OrcaFlex, and something which is suggested in the singular Jacobian error message we saw earlier. When this model is run with the line connection offset removed, we note that the error message offers the suggestion that the error might be resolved by using a very small Jacobian perturbation factor. This factor is a non-dimensional number that adds in a small additional contribution to the diagonal of the Jacobian matrix, taking away the singularity and allowing it to converge. This helps resolve convergence problems for which there might not be a physical solution. The Jacobian perturbation factor is found on the Jacobians page of the general data form. It has a default value of 0, as the preference should be to find a physical solution wherever possible. If a physical solution, such as the negligible line connection offset, cannot easily be found, then we can add in a small value here instead. For example, setting this to 1e to the minus 12 is enough to provide a solution in this case. It is important to read the documentation on this subject, accessed from this page by clicking the question mark at the top right or pressing F1, to make sure you understand the implications of applying a non-zero value. That finishes our discussion on the buoy objects. In the next video, we will be looking at constraints.